Alright, so here's our question. So how would we summarize this info? We've got a brick. Well, so we've got mass is equal to, so here's our first example. We've got a brick, mass is equal to 1. So this is, okay. Equation of motion, x double dot is equal to 10 minus kv squared. Cool, and we're told that the terminal velocity is 2 meters per second. Find k. And part B, how deep does it reach until we get 90%? Find x, I suppose, at 90% of v sub t. So also initially, I guess you can say at x equals 0, v is equal to 0. That's probably something you can infer from the diagram because we've got a brick at the surface of the water, 1 kg. We're dropping this dude. I think you could assume that at x equals 0, v equals 0, so you need that for the question as well. So we're talking about terminal velocity. When did we say terminal velocity actually occurs?
A is 0.
Yeah, right. So it's when the acceleration is 0 because it means the velocity is not changing anymore, right? So we can just say, all right, at a is equal to 0, or in this case, x double dot equals to 0, right? Then that's our acceleration. So 0 is equal to 10 minus k v squared. But then what is the terminal velocity? Well, it's 2 meters per second, right? So you also have that the terminal velocity is equal to 2. So we can replace that with 2 as well, okay? And then we can just solve for k in that way, yeah?
Which is
3.5, right? So that's, they often refer to that as the constant of proportionality. You might remember that from linear variation. And they do use that term here and there for this value of k that you're often finding. So that's your resistance coefficient or something like that, right? Okay, so that's part A. Part B, right? Find x at 90% of v sub t. So remember when I said that the difficult part of mechanics is choosing the right acceleration form, because we have a few different forms, right? We have that the acceleration can be equal to dv dt, or what was the other one? Acceleration could be equal to dv dx, v dv dx, remember that one? Yeah, okay. So there were those two forms there that we could have used. And it's how do you know which one you want? Well, it depends on what you're trying to find. If you're working with displacement, then often you will probably want to use this form over here, which is the one that's going to be helpful for you, right? If you want to work with time, then you will use something like this. The other thing to consider is, okay, we want to find 90%, find where the 90% of terminal velocity occurs. Well, we need to know what 90% of terminal velocity is, first of all. So that's 0.9 of 2, so that's just 1.8. That's all well and good, right? All right, so now we can sort of construct this equation that we're working with here. So we have our equation of motion for acceleration is x double dot is equal to 10 minus, now we've got k here, 2.5 v squared. And then we say, all right, well, because I'm working with displacement here, I'll replace this with v dv dx equals to 10 minus 2.5 v squared. And you can start to see where the integration is going to come into play, right? Because the idea is, okay, we want to actually integrate this expression to find velocity in terms of x, and then we can sort of work with this and substitute some values in, right? So what rearrangement might you want to do here? So what kind of differential equation does this resemble, do you reckon?
Could do, what's it called? Log.
Yeah? How did you do that? How did you get it looking like a log?
Put it all to one side.
So divide by here.
Yeah, with the x on the side.
And dx on the other side, good. And remember, when you are treating it like a fraction, the dv dx, basically you're always going to be wanting to integrate at some point, right? And you're right, yes, this is of the log form. What do we need to multiply though by? If we want that form, where we have the derivative on the numerator as well. So basically, what's the derivative of this guy?
5.
So 5, so 2 times negative 2.5, so negative 5 we want. So put 1 on negative 5 outside. And then we can integrate, so we get on this side over here. Now, there's a trick which you guys are allowed to apply when you're doing something like this. And it's basically a shortcut for the bounds where you have initial conditions. So the idea is, if for example you have some initial conditions, so like we know x equals 0 and v is equal to 0 here, right? And we also know that we're trying to find when the velocity is at 1.8. What you can do is, a trick you can apply is, if you have the lower bounds, you can sort of put them in. So you know you're going from 0 to 1.8 for velocity. And this one you kind of cheat a little bit. Like basically, if you're trying to solve for this variable, you can kind of go from 0 to x, right? So, but remember, in density functions, there's an issue with like using that variable there, so they may replace that with like some other thing. Like t is a bad example because it's time, but they may use some other variable for that. But that's a trick you guys can use in this kind of situation. So just to see how that works, we can do it with the initial conditions first, but then you can see that it will work if you just substitute in the bounds as well, right? But I'll show you that in a second. So that's just something to be aware of. Yeah. So you can do this trick where you just go from you turn the initial value problem into a definite integral, and then you save a bit of time doing that. Yeah, there's a way to show that it actually works, but I'll come back to that one at the end when we do this. So let's just do the integration first. So negative 1 and 5 log 10 minus 2.5 v squared is equal to x plus c. And then so we know at x equals to 0, v is equal to 0, right? And so we get what, negative 1 over 5 ln of 10 is equal to x. And so what's my x going to be? My x is going to equal to, x minus 1 and 5 ln of 10 is equal to minus 1 and 5 ln of 10 minus 2.5 v squared. And, sorry?
Did you mean c?
Isn't it C? Oh, right, sorry, C. Yeah, you're right. Thank you. Good pickup. That all good?
Yes.
Yep. Okay, so then x is equal to negative 1 on 5 ln of 10 minus 2.5 v squared plus 1 on 5 ln of 10. So we're trying to find x at 90% of the terminal velocity, right? And we already found out when that occurs at 1.8 meters per second, right? So then all you have to do is just substitute in your values for x. I don't know why there's no equal sign here. Should be an equal sign here. So x is equal to then minus at v is equal to 1.8, negative 1 and 5 ln of 10 minus 2.5 times 1.8 all squared plus 1 and 5 ln of 10. Go ahead and calculate that for me. You put it in for me, Angus?
0.33.
Yeah, that's fair, right? So when you put that in, 0.33. So what is that really saying? It's saying at 0.33 meters, it reaches 9% of its terminal velocity. Just to show you that this trick works over here, so the idea is that your lower bounds match up with the initial conditions. So it was at x equals 0, v equals 0. And then we're looking for what happens at v is equal to 1.8. And then here we kind of cheat a little bit. The upper bound is kind of like, just like x, basically, right? So what it ends up becoming is, well, this becomes x over here. And in this side, what are you going to put in? Well, you've got negative 1 over 5 outside the whole thing. and then you've got the integral of this. So this is ln of 10 minus 2.5 times 1.8 squared. I'm running out of room here. Take away ln of 10, looks like. Yeah, so when you integrate this and then substitute in v is equal to 0, right? And so you can see that that's equal to the same thing as up here. Was it this line? Right? When you expand it back out, right? So this is like a trick to save you a bit of time. With initial value problems, you can change it into a definite integral problem when you're doing this. So they tend to do this a lot in your textbooks and work examples and stuff like that. So just kind of be aware
So we
of
can
that.
do it with an example.
Yep, that's fair game.